In this video, we're going to have a brief introduction to molecules known as aromatics. We're going to talk a wee bit about nomenclature and the drawing of them. It's pretty straightforward, and the expectation is not huge. There's not a lot you need to know about these, but it is good to be introduced to them. So why don't we get started? Just a little bit about the term. So the term came about historically due to the observation that many benzene derivatives, we'll see what benzene is all about in a minute, many of these derivatives are known to be pleasantly fragrant. Now, I've had a few experiences with aromatics as well, and most of the ones I've come across have not been pleasantly fragrant at all. Aromatics can be very complex, but I want you to focus in on benzene and a few benzene-containing molecules and how to deal with benzene as a branch. And then I will ask you to come to terms with a few benzene derivatives or aromatics that go by the common name, but you'll see these common names are very common, and hopefully you'll pick that up quickly. So let's carry on. So benzene has a chemical formula C6H6. So if you're to try to draw benzene, well, let's have a go. 1, 2, 3, 4, 5, 6. There's my 6-carbon chain, C6H6. All right, so let's try saturating with 3. So that's 3. Now I have 3 to go. 1, and already I'm out of hydrogens. I can't draw it as a straight chain, and there's no possible way to draw benzene C6H6 like a straight chain. Well, how about as a ring? Well, let's try that. Okay, so 1, 2, 3, 4, 5, 6. Whoops, not the greatest ring. So there we go. So H2, 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 and already again, no more hydrogen. So I'm stumped. So the structure of benzene, and the reason I'm mentioning this was a puzzle for quite a long time, the structure of benzene. And what happened was a gentleman named Kekuli had, again, the legend has it, he had a dream that he was working on benzene, and he had a dream that the benzene structure must have been like, he came up with this notion that it looked like this Urubura. So this is a mythical dragon eating its own tail. It means a lot of things in a lot of different sort of ancient societies and cultures, but Kekuli used it to come up with a structure for benzene. And so this is actually from his paper, and so you can see from the structure this represents a double bond, C, double bond, C, and because it's double bond, there's going to be a single H there. Well, here's another carbon-carbon double bond with a single H. So that structure, the Kekuli structure, gives rise to a plausible formula for benzene, or structure for benzene, alternating double bonds. But what it does mean, though, is there must be another structure where the double bonds are on different carbons, start at different carbons. So here's the alternating structure. So this, for a long time, was the common way to represent benzene. This is known as resonance. If you have the same molecule with different structures, they're not really isomers because they occur in equal amounts, basically. So this is known as resonance. So anyways, Kekuli structure. Quite an interesting story behind that. So different ways to show it. So again, there's the Kekuli structure. Well, we can also show it as resonance, and so if you're using the Kekuli structure, you must show the resonance, and so that's how resonance is, this double arrow between the two possible molecules. And that's the only possible orientations for benzene. Another way to show it is what's known as the aromatic structure, and so the whole premise here is that these electrons of the double bond, because they can be on in any orientation almost, are actually delocalized electrons. And so this circle just indicates you have individual electrons flitting around, satisfying the bonding of all 6 of those carbons in the ring. So aromatic structure is one way to show it, and then we simplify that like this. So line structural diagram for the aromatic. You very commonly see that for benzene because it's a simple way to show it, and every chemist will recognize that as a benzene. Benzene naming, it's pretty straightforward. Just like we've always done, you identify branches around a benzene. So benzene, again, is going to be the main molecule. So there's my benzene. and I look at branches. And so I have a 1-carbon branch here. This is a line structure diagram, and I have a 2-carbon branch here. So that's an ethyl branch, and that's a methyl branch. And then just all the rules you've gone through apply. And we position, so it's a ring, we position to minimize the numbering. We're going to list it alphabetically, so we must still start with ethyl first. So on carbon 1 will be ethyl, carbon 3 methyl, benzene. So there we go. 1, 2, 3, propyl benzene. Remember, you don't need the number on a ring structure if there's only one branch, because it will always be carbon 1 of the ring. That will always be carbon 1 for benzene. So benzene is not really that much different in terms of nomenclature, unless we treat benzene as a branch. And so in some instances we can look at benzene as a branch, and if it's a branch, it's known as a phenyl branch. Notice the YL ending? That's what tells you it's a branch. Phenyl, YL, just like alkyl. And so if we treat this, we've seen this molecule already, that was propylbenzene. Well, now let's treat it as a branch, the benzene as a branch. So we still have our propane. So there's propane 1, 2, 3, and so the phenyl branch is on carbon 1, and so we do have to number 1-phenyl propane. Now, it's probably not very often done that way. It's more likely going to be called phenyl benzene, or sorry, propylbenzene. But that's how you could deal with benzene as a branch. So let's look at another. Here's another example, 1,3-diphenyl cyclobutane. Well, that looks like a mouthful, but it's pretty easy to pick it apart. So it's a cyclobutane, so cyclic 4-carbon, and on carbon 1 and carbon 3 you have a benzene bonded to it, a phenyl branch. So let's have a look at what that is. And so that's the structure. But when I plug this into my fancy organic molecule software, I get this name. And so this is actually the real IUPAC name. You don't have to worry about this, by the way. If you named it this way, that would be more than acceptable for me. But just see how this works. So again, what we're saying here is the main thing is a benzene. So which one is it? Well, it doesn't really matter. So let's pick this as our benzene. And so this is a branch. And you see how this becomes a branch? Cyclobutyl, YL. So there's my cyclobutyl component of the branch, bonded to carbon 1 of the benzene. That's why there's no number for this whole branch. But that's the cyclobutyl component. So cyclobutyl comes from this bit. And then the 3-phenyl. So now we have a number and the phenyl. And the 3 is because it's on carbon 3 of the cyclobutyl branch. And so 3-phenyl is this part, bonded to carbon 3 of the cyclobutyl. So again, there's always going to be slightly different ways to name things, and the whole point I try to make to you is as long as you're systematic about it, you're going to probably come up with a name that is acceptable. Alright, so 1,3-diphenyl cyclobutane works, and 3-phenyl cyclobutyl benzene also works. Let's carry on. Another type of way to name benzenes is something known as orthometa-para designation, and for our purposes we're dealing with two branches that are the same. Okay, so when we have two branches that are the same, we can simplify it a little bit. So this is the ortho designation, ortho, and so we can name that now, and if you notice there's benzene and these are methyl groups, so we can call it ortho dimethyl benzene. Well, why didn't we just call it 1,2-dimethylbenzene? It's actually quicker. Well, it is. So this is often shortened to ortho, as in O dimethylbenzene. Okay, so ortho dimethylbenzene, O dimethylbenzene. And so here we have two fluorines. So that is not ortho because they're on different, bonded to different carbons of the benzene, and so this is meta designation, and so that would be M difluorobenzene. And so obviously this last one, again, two methyl branches, that is para, and so that's P dimethylbenzene. So ortho, meta, para designations, remember they have to be the same branches, have to be the same type. So those are both methyl branches, those are both fluoro, those are both methyl. So as long as they're the same, you can use ortho, meta, para if you like. Just a couple more examples. So here we have a benzene, and it's a 1,2 carbon branch. Those are both ethyl branches, and so that is P diethylbenzene. Same as 1,4 diethylbenzene. Ortho dipropylbenzene. So ortho is where they're next to one another. So let's draw a benzene. There's our benzene. Aromatic structure. Ortho next to each other, doesn't really matter where you put them. So it's propyl. So there's carbon 1 of the prop, 2, 3. Carbon 1, 2, 3. So there's ortho dipropylbenzene. Now, just for a couple of common ones, and so these come up fairly often. This is a very common derivative of benzene. It's known as toluene. And so what is toluene? The systematic name for toluene would be methylbenzene. But it is so common. It's a very, very common precursor to a lot of different types of aromatic synthesis reactions. And so methylbenzene is given a common name, and that is toluene. And so I'd like you to know that as toluene. Methylbenzene is toluene. Here's another one, and I'm sure you've come across this in your travels. Do you recognize what that is? That's actually polystyrene, styrofoam. And so this is the precursor to that, this benzene derivative. And so what we have here is a phenylethene. Sorry, phenylpropene. So phenylpropene is the systematic name for that. You don't need numbers because there's only one way to attach that to the propene molecule. You can't attach it on carbon 1 or 2, and that is given the common name styrene. So hence polystyrene. So what we do, we take this molecule, we make it a macromolecule, we polymerize it, but that's for another conversation. A couple more to finish. Here's one, again, you may not recognize this right away. Notice the toluene component. There's a benzene with that single methyl group. So that's a toluene precursor. And then we add a couple of nitro groups, and we get trinitrotoluene, TNT. So trinitrotoluene, very reactive chemical. It's not the same as dynamite, by the way. And the last one, this is what I mean by not necessarily being fragrant. So mothballs. And mothballs, there's the formula or the structure for mothballs. Mothballs are definitely not fragrant, and they're certainly not fragrant for moths. And so this is given the common name of naphthalene. And again, I punched that one into my name generator for organic compounds, and it came up with naphthalene. So this is definitely known as naphthalene. So there's your brief introduction to aromatic compounds, mainly benzene and benzene derivatives. Benzene is a branch. So that concludes this video.